Okay, in the previous video, we were talking about function transformations, and we covered translation, so horizontal and vertical shifting. And here we're going to pick that up, and we're going to start with dilation and compression. In other words, what we call scaling or rescaling, okay? Here we have really four kinds of scaling, and something to keep in mind here, that whenever we write the number c is going to be a positive real number greater than 1. Okay, so think 2, 5, whatever, right? When we do that, then it'll be easier to think about how we're actually dilating or compressing by a factor of a real number, okay? Or sorry, you get what I mean. It's a real number. It's positive, and it's greater than 1. Okay, so the first kind that we discuss here is, again, we're going to start with the vertical version of both. All right, and so we have two fundamental types. All right, so we're going to dilate by a factor of c. So we would write g of x equals c times f of x. So this is what we would call dilation by a factor of c, or stretching vertically. Okay, that was a little messier than I intended. The second type is if you're instead multiplying by the reciprocal of c, so you're actually multiplying by something smaller than 1. Now you are, did I get this right? Yes, I did. Okay. Now you are talking about vertically compressing by a factor of c. This is now shrinking. Okay, so there's a lot of words here, but remember, all we're doing is we're either going to be stretching or compressing by a factor of whatever c is. Okay, so let's see an example here, a prototype, if you will, of what we're trying to accomplish here, right? So for this example, we're going to think about something that looks like this is actually going to be the square root function, okay? So it passes through the points 1, 1, and I guess I should put 4 here. And it passes through 4, 2. So this is the square root function, oh boy, f, okay? And we're going to apply two different kinds of vertical scaling. So in the first, I'm going to stretch f into g of x equals 3 times f of x. And the second one will be h of x equals 1/2 times f of x. Okay, so what does g of x do? It's going to be stretching it by a factor of 3. So it stretches it so much that we actually, can't see the graph anymore after x equals 1. And notice what it's really happening here is we're just multiplying the y values by a certain factor. So in this case, we're multiplying the y value 1 by 3. On the other hand, multiplying by 1/2 gives us the point 1, 1/2, and the point 4, 1. So here's the function h. Here's g. You can see how when you are vertically compressing or shrinking, you get something that's below f, and when you're stretching, you get something that's above f. So our key insight is we're just going to change our y values by only change our y values by multiplying or dividing, okay? Our second type is horizontal rescaling, and again, this isn't going to fit the mold that you expect it to. We're going to have to do the opposite of what's inside the parentheses for the function statement, okay? So what we're going to do here is our first one, our g of x that we obtained from f of x. G of x is going to be f of x divided by c. And what does this yield? This gives us again, dilation. Dilate horizontally by factor of c. So this is stretching. And you wouldn't believe that because what we're actually doing is we're dividing x by a number. This is the opposite of what we expect. H of x being f of c times x is instead going to give us a compression by a factor of c. So in other words, this is kind of like in opposite of what we had before. Instead of multiplying by c and we multiply 1 over c, we're either multiplying by c or 1 over c, but backwards, okay? All right, so let's see an example. Yeah, drawing out these graphs, it's getting real tedious, but I guess I asked for it. Okay, so my original function, I'm not even going to describe it. I'm just going to say it's some function that looks like it's passing through 0, 1. That's, yeah, 0, 1. Passing through 1, 2, and passing through -1, 2. So, and I'm going to say it looks like this. So not quite a quadratic something else. All right, so that's my f. And then I'm going to obtain from f the two different kinds of functions that result in horizontal rescaling. The first, g of x, is going to be f of x over 3. And then the second will be f of 2x. So importantly, what is actually going to happen here? So when we are horizontally scaling, we're changing the x values, right? Opposite of what inside the parentheses it says. So for g, we're going to multiply each x value by 3. And we're not going to change the y value, okay? So here's that one. Here's that one. And so it should look like this. I should have written that somewhere else, but here's g, okay? Remember, the y values aren't changing. The x values are. Now, h, we're gonna actually divide our x values by 1/2, or multiply by 1/2. Again, that doesn't change this point, but what it does change is these points, because now we're going to take 1/2, 2, and -1/2, 2. And so that should look like this. Okay, not super great, not a very accurate picture, but the key insight is change the x values in the opposite way of the desired transformation, right? So, e.g., f of 2x means divide each x value by 2, and vice versa. Okay, our last kind of transformation is reflection. And reflection is actually much easier than what we've been doing here. So there are two types that we discuss here. So our first type is vertical reflection across the x-axis. So we do g of x equals negative f of x. This will result in reflection about the x-axis. And the second type is h of x equals f of negative x, which is, you might have guessed it, reflection about the y-axis. And of course, we can actually we can modify these, generalize them so that we're reflecting about an arbitrary axis, but we're not going to get into that right now. However, let's think about what this would look like, right? So here's please ignore my dog. She's getting old and she's tends to bark at anything. Okay, so again, setting up my axis here. And represent each kind of these transformations. All right, so this function, which I'm not going to name, is going to pass through a few different points. So it's going to pass through 0, 0. It's going to pass through 1, negative 1/2. And it's going to pass through 2, 1. And it looks like this. So again, this is 1, negative 1/2, and this is 2, 1, and this is 0, 0. Okay, so if I want to reflect about the x-axis, right? So g what I'm going to have to do is each y value, I'm just going to change its sign. So 0, 0, the y value 0, change that to 0. That doesn't change. But then 1, negative 1/2 means that it's actually going to be 1, 1/2. And then 2, 1 means we actually are at 2, negative 1. So it'll look like this. Okay. Now together they kind of make this little fish shape, and that's kind of cool. What about h? So if we're going to reflect about the y-axis, now we're changing the x values, and again, just change the sign of the x value. So again, it's easier. So 0, 0 is going to still be 0, 0. 1, negative 1/2 is going to be negative 1, negative 1/2. And then 2, 1 will be negative 2, 1. So what that actually ends up looking like is like this. That's not perfect, but you understand. Okay. One really cool thing about reflection, okay, is even functions not affected by reflection across the y-axis. And this makes sense, right? Because if you're going to be changing each y value so that it's on the every x value so that's on the opposite side of the y-axis, it already has that going for it because it's even, right? We know that for all x, f of negative x is equal to f of x. So that ends up being really cool. So more generally, though, we should keep trudging along, and we're going to talk about transformations generally. Because while it's true that we are, each transformation on its own is fine, but we are often doing multiple at once. Okay, so what we mean then by that is, in order to get f and some new function g, sometimes we have to apply a couple of different transformations. And this isn't an accurate representation of what we're talking about, but it's possible that along the way that you have to apply different transformations, and that does different things to the function. Okay, so you may be stretching, you may be dilating, you may be shifting and reflecting at some point. The only thing that is really important here is you have to do this in order, right? So look at the function, what it actually means, okay? And you're going to apply each one in order, and I'll show you what that means in a second. So here are the examples that we're going to work on, okay? So first, okay, we're going to write the function statement for the combination transformation. So write the function given some function f that does this. So step 1 is a horizontal stretch by a factor of 3. Step 2, we're going to reflect across about the x-axis. Step 3, we're going to vertically shift down half a unit. Okay, so let's think about what exactly has to happen to. So we have some f of x that can be whatever, right? Whatever it happens to be, right? What step 1 will do is we'll say we're now going to have this new function, intermediate step, I'm not going to label it, where we horizontally stretch by a factor of 3. So what that means is we're going to actually end up using f of 1/3 x. Because remember, that's how we can represent a horizontal stretch by a factor of 3. Step 2 means that whatever this is, we're now going to reflect across the y-axis, the x-axis, and that means we're going to make it negative. Notice the order matters here in the sense that we are applying the stretching first, because what comes next is going to be the vertical shift, which is, now we're going to subtract 1/2 from this. And this is our g of x. So this is actually our answer. So this is the general statement for this transformation that does all 3 of these things in that order. Okay. Next, let's describe y equals 2/3 x minus 1 to the 4th as a transformation, or really a sequence of transformations, of y equals x to the 4th. Okay, so how do we get this new function from x to the 4th? Well, our first step is, so remember, work your way from the inside out. So the very first thing that you're doing is actually you're going to horizontally shift right 1 unit. That's how we accomplish this. Okay. And then our second step, whoops, not what I wanted. Our second step is to multiply by that factor of 2/3. So that's a vertical rescaling by 2/3 factor. Notice that if we're multiplying by 2/3, that means that's something smaller than 1 but greater than 0, which means we're actually compressing. Okay, so that's exactly what we're doing to the graph of y equals x to the fourth by applying this. Okay, our last example here, which is perhaps the most essential one here, okay, is we're going to graph the function f of t equals 2, sorry, I didn't want that parentheses there, sine of 3t minus pi. Wow, that's a lot going on there, right? So what do we want to do here? We want to identify how we get this from sine of t. So let's think about this. Our parent function is y equals sine of t, which we know how to graph. We've covered this. And let's think about what we need to change or what we need to transform in order to obtain this final function. So step 1, remember, move from the inside out. So the very first thing we're doing is we're going to apply a horizontal compression by factor of 3. Because that's the very first thing that happens to the value t. Sorry, to the variable t. Or that's, our function is doing something to an input, and our input is t. 2, we're going to horizontally shift right pi units. Okay, so that covers now this and this, right? Then the last thing is so obviously we're applying sine, but we're going to be, after that, this step right here is going to multiply by 2, so that's a vertical stretch by factor of, or dilate, factor of 2. Okay. Whew, that's a lot. So there's 3 steps here, and there could be arbitrarily many, but we're going to do our best to, and I'm actually not going to use this tool, never mind. I'm going to try my best to fill out, oh boy, here we go. Okay, so here's pi, here's 2 pi, 3 pi over 2, pi over 2. And when you're setting this up, one important thing to note is when you're compressing or dilating, you want to make sure you can represent all the important values, not only in terms of the original points, but also the multiples of that factor, right? So if we're ultimately going to have to divide by 3, then let's throw in pi over 3, 2 pi over 3, etc. So here's pi over 3. 2 pi over 3 is around here. Then we're going to put in 4 pi over 3 and 5 pi over 3. So it's not super accurate, but more or less that's what we have. Okay. And then remember that since it's a sine function, originally our points are, I'm going to use just black for now. to represent the original function, sine of t. So it starts at 0, 0, goes up to pi over 2, 1, pi 0, 3 pi over 2, negative 1, and then 2 pi. So it looks like this. So this fundamental shape, somehow we're going to reapply by doing these transformations. So the first thing we do is we horizontally compress this by a factor of 3. What this means then is, one thing you can do here is we can take first the pi and the 2 pi points. So it's going to cross at pi over 3 and 2 pi over 3, okay? And then halfway mark there, and halfway mark there. So our first step here is to represent this function like this, okay? And then we can keep going, actually, because it's gonna keep going. So it should look like this, this, this. Okay. And again. Okay. So I'm going to do my best now to erase the original graph. And I'm just going to work with this new green graph, which is an intermediate step. Remember, this is step 1, right? I'm going to use a different color now to represent the next step, which is a horizontal shift right by pi units. So every point now is shifted right pi units, okay? So we're actually starting from here, going up here, down here, down here, down here, up here, here, etc. Okay, so now it looks opposite, and we can fill in backwards as well. So it should look like this, that, that, this, that, that. Okay, so that's step 2. And again, I'm going to erase our green curve now, because that's an intermediate step that we don't need anymore. Now we're on to the last step, which is let's graph how we can vertically stretch this by a factor of 2. And now this is going to be our final graph. This is the actual graph of the function that we want. So every point that has a y value of -1 is now a y value of -2. Every point that has a y value of 1 has now a y value of 2. And now we can fill it in. And that's how we get this transformed function from sine of t. And this follows in that what we're doing here is we're actually taking, so remember f of t equal 2 sine of 3t minus pi. Remember, what we actually were obtaining here was an amplitude of 2. So that's how far away the sine curve gets away from the midline. We had a angular velocity equal to 3, which tells us something about the period, namely that the period is going to be 2 pi over 3 instead of 2 pi. Lastly, our phase shift is pi. And when we phase shift by pi, we often get something that looks like cosine instead of sine. Obviously, this is a reflected cosine. And so we can predict this much more quickly if we have some prior knowledge of how trig functions work. But ultimately, it comes from function transformations.